Imagine being able to rewind the history of the cosmos as if it were a film, frame by frame, until the first lights begin to seep through the primordial darkness. For decades, scientists believed they knew what they would see in those opening scenes: chaotic gas, sketchy structures, nothing truly organized. Today, thanks to the James Webb Space Telescope, we have finally ventured that far. And what we see does not resemble the script we were expecting. Instead of a still formless universe, we find galaxies already compact, luminous, and surprisingly mature. One of the first to shake our theoretical confidence was named Glass Z13, a galaxy that appears when the universe was only a few 100 million years old. At that epoch, according to traditional models, we should only observe galactic embryos, small clumps of stars struggling to stabilize. Glass Z13, however, looks like a system that has already undergone a long evolutionary journey. And it is not alone. As James Webb has gathered more data, the list of galaxies that are too big, too bright, too orderly, and too early has grown embarrassingly long. As if that were not enough, some of these galaxies show a disk structure, sometimes with arms reminiscent of classic spirals. Exactly where we expected inefficient, turbulent chaos. It's like finding cities with skyscrapers and perfectly designed roads in a world that should still be populated by villages of huts. The result is always the same. Simulations based on our standard models struggle to produce such orderly structures in such short timescales. Then came another anomaly, objects like Sears 1019, a primordial galaxy hosting at its center an unusually active and already massive supermassive black hole. Here the problem is even more delicate. We know black holes can grow by devouring gas and stars, but there are physical limits to how fast they can do so. To reach the mass of these objects in the few million years available after the Big Bang would require extreme and nearly perfect conditions, or black hole seeds born already enormous through mechanisms we do not yet understand. It is within this scenario that cosmologists like Andrzej Kusiu raise their voices. According to him, the universe that James Webb is revealing is faster, more creative, and less well-behaved than traditional models have led us to believe. Equations like those of general relativity are not wrong in themselves. They still describe gravity perfectly in many contexts. But the idea that they are sufficient on their own, embedded in a linear and predictable cosmological model, is beginning to show its limits. If complex structures arise so quickly, perhaps what we considered the exception is actually the rule. For decades, we have patched cracks in the standard model by adding invisible yet mathematically convenient ingredients. When stars in the outskirts of galaxies rotated too quickly, we introduced dark matter, a form of matter that emits no light, does not interact with electromagnetic radiation, but exerts gravity. When the universe's expansion was found to be accelerating rather than slowing down, we added dark energy, a mysterious cosmic pressure that pushes space itself to expand faster and faster. The picture that emerged looks elegant on paper. About 5% of the universe consists of ordinary matter, the kind that makes up stars, planets, and ourselves. While the rest is made up of dark matter and dark energy, entities we cannot see directly but infer from gravitational effects and cosmic expansion. A powerful theoretical framework, capable of explaining many observations, yet one built on components never directly detected in the laboratory. Kusiu and other researchers do not deny the successes of the standard model, but they highlight its conceptual fragility. If 95% of the universe's content is dark and undefined, how solid is our sense of control over cosmology? And if, despite these added ingredients, anomalies like hypermature galaxies, overly fast-growing black holes, and spiral structures in an era that should be ruled by disorder continue to emerge, isn't that a sign that we might be seeing things from the wrong perspective? One of the most intriguing, and at the same time most technical, cracks is the so-called S8 problem, which Kusiu considers a privileged indicator of inconsistencies in our way of describing the cosmos. S8 is a parameter that essentially measures how clumpy the universe tends to become. That is, how much matter clusters into structures like galaxies, galaxy clusters, and cosmic filaments on intermediate scales. The higher the S8 value, the stronger this tendency to cluster. Scientists determine it mainly through two methods. The first looks at the oldest echo we have of the Big Bang, the cosmic microwave background, a fossil light dating back to when the universe was just 380,000 years old. By analyzing the minute temperature fluctuations in this light with extreme precision, it is possible to infer the contents and structure of the early universe and, through models, predict how clumpy it should be today. From this, one obtains a certain value of S8. The second method instead observes the late universe, the one we see now, by measuring how the light from distant galaxies is slightly distorted as it passes through the web of matter distributed across the cosmos. This is the phenomenon of weak gravitational lensing. The gravity of all the matter along the line of sight acts like an imperfect lens, stretching and warping images. By statistically analyzing these distortions across millions of galaxies, scientists can deduce how much matter has actually clustered over billions of years. And here lies the problem. The predictions derived from the cosmic microwave background suggest a universe more clumpy than what is observed through gravitational lensing. In other words, S8 does not agree depending on how it's measured. Statistical uncertainties are no longer enough to explain the discrepancy. It has become a real tension, the so-called S8 tension. According to Kusiu, this very tension is closely linked to what we see in the primordial cosmos thanks to James Webb and leads to an uncomfortable question. If the numbers don't match, is the universe cheating, or are our models incomplete? To truly address this question, Kusiu does not stop at admiring the spectacular images of the first galaxies. He dives into the most subtle details of cosmic structure. One of the most refined tools we have for this purpose is the so-called Lyman alpha forest. When the light of a very distant quasar travels across billions of light-years of space, it encounters along its path clouds of neutral hydrogen scattered throughout the intergalactic medium. Each time the light passes through one of these clouds, a specific wavelength is absorbed. As a result, the quasar's spectrum appears dotted with hundreds of thin dark lines, a forest of imprints left by hydrogen. These absorption lines are not mere spectroscopic curiosities. They contain information about the distribution of matter at great distances and high redshifts. By analyzing their statistics, scientists can reconstruct how matter was distributed when the universe was only a fraction of its current age. The Lyman alpha forest thus becomes an indirect map of the primordial cosmic web. It shows where structures begin to form, how dense they are, and how quickly they grow. It is precisely on these measurements that the great DESI project comes into play, the dark energy spectroscopic instrument. Imagine a telescope whose pupil is connected to thousands of extremely thin optical fibers controlled by tiny robots. Each can target a different galaxy or quasar and capture its light simultaneously. In this way, DESI collects, in a single exposure, the spectra of 5,000 celestial objects. Repeating this process night after night, it builds a gigantic three-dimensional map of the universe extending across billions of light-years, recording not only the positions of objects but also their redshifts, that is, their distance in time. Originally, DESI was designed to measure with great precision how the universe expands over time, exploiting baryon acoustic oscillations, a kind of cosmic ruler, engraved in matter distributions. But the same data, when analyzed through the lens of Kusiu and other theoretical cosmologists, also allow them to probe the properties of dark energy and test whether its influence remains constant or changes throughout cosmic history. The first results suggest that the universe may be more complex than a model with perfectly constant dark energy envisions. Some analyses indicate that parameters such as the rate of expansion and the way structures grow over time might be compatible with a cosmos slightly older than previously thought. Not 13.8 billion years, but something closer to 15 billion. A greater age would give galaxies more time to organize and black holes more time to grow, easing the tension created by James Webb's impossible galaxies. But Kusu's interpretation goes beyond simply adjusting the cosmic clock. According to him, the enormous discrepancies among certain data, from the S8 tension to overly mature structures in the young universe, suggest that we may have built our cosmology on overly rigid assumptions. Perhaps the error lies not only in estimating the age but in the very idea of a space-time that expands uniformly and smoothly, governed by gravity that behaves the same way everywhere. Here, more radical models come into play, such as the one in which the cosmic horizon grows in direct proportion to cosmic time, a scenario often expressed as RH equals quart. In a universe of this kind, the overall dynamics of expansion are simpler and more linear, but the consequences for the evolution of structures and the interpretation of observational data are profound. Some of the oddities seen by James Webb and in S8 measurements seem to align better with a cosmos that follows this alternative expansion law rather than the standard model. Of course, these models are not universally accepted. Every time the rules of the game are changed, one must ensure that the new rules still explain the immense body of data the previous model successfully accounted for. Yet it is precisely in this tension between conservation and revolution that science takes its most important steps. Kusu argues that continuing to add fixes to the standard model, more dark matter, slightly variable dark energy, adjusted parameters, risks turning cosmology into an exercise in fine-tuned accounting rather than a quest for deeper truths. Another fascinating possibility emerging from his work is that space-time might not be smooth and continuous at all, as we have always been told, but possess a more complex structure, perhaps discrete, layered, or even fractal. In such a cosmos, gravity would not be a static, uniform force, but an emergent, capricious phenomenon that behaves differently at great distances than it does near the solar system. A sort of gravitational weather, with regions where space expands and curves in ways that can no longer be described by a single equation valid at all scales. Instruments like the Lyman alpha forest, DESI's spectroscopic mapping, and James Webb's direct observations are therefore playing complementary roles. On one side, we see directly what exists: galaxies, black holes, and structures that should not be there so soon. On the other, through filtered and distorted light, we reconstruct how space-time deformed to allow those structures to arise. It is like observing a city at night from above. The lights of the buildings tell you where life is, but only by studying the roads, bridges, and pathways connecting them can you truly understand how the city functions. For Kusu, the primordial universe emerging from this combination of data is not a chaos that slowly organizes itself but an already structured, creative, multi-layered environment. In this scenario, dark matter as an invisible, perfectly stabilizing agent may have been an elegant but mistaken, or at least incomplete, hypothesis. Likewise, dark energy might not be a mysterious constant uniformly filling space, but rather the symptom of a cosmic geometry more intricate than what standard general relativity can describe. If these ideas prove correct, the consequences will extend far beyond cosmology. They would change our understanding of nature, matter, and even the very concept of time. The idea that the universe follows a deterministic, perfectly predictable script would be replaced by a vision in which creativity, instability, and surprise are not flaws of the model but fundamental features of the cosmos. And the current crisis, instead of a collapse, would become the opportunity for a new scientific revolution, one on par with the one Einstein began over a century ago. In the end, the message implicit in Andrei Kusu's words is this: it is not the universe that has gone mad, it is we who have grown too attached to our formulas. James Webb, DESI, the Lyman alpha forest, and all the instruments we are building are simply reminding us of that. The cosmos is faster, bolder, and more creative than we ever dared imagine. And if we have the courage to accept it, we will have to rewrite the history of the universe from scratch, with new, more flexible models, finally capable of embracing all the complexity that the sky is showing us. If you've made it this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.